Welcome back to Hansen Theory. So far, you have learned molecular forces, Hansen space, Ra distance, red number, polymer behavior, and solvent blend design. Now, we move into the next critical dimension, pigment-resin interactions. Because pigments are not passive fillers. They are active participants in the molecular game. And understanding their behavior through Hansen theory is what separates average engineers from minority-thinking engineers. Let's start with a common misconception. Many engineers treat pigments as inert. Just grind it in, add it to the resin, let it disperse. This approach works sometimes, but when formulations fail, pigments are often the culprit. Flocculation, floating, settling, color inconsistency, opacity problems, all trace back to molecular interactions. Here's the key principle. Pigments have surface energies, not just color. The surface of a pigment particle interacts with resins and additives through the same molecular forces we have been discussing: dispersion, polar, and hydrogen bonding. If the forces between the pigment and resin do not match, the system becomes unstable. Hansen theory allows us to quantify this. We place pigments and polymers as points in Hansen space. The distance between them predicts wetting, dispersion, and stability. Let's break this down. First, dispersion forces. Pigments with large nonpolar surfaces interact through dispersion. Nonpolar resins will wet these pigments effectively. Mismatch and dispersion leads to weak adhesion, pigment floating, or sedimentation. Second, polar interactions. Pigments often have surface functional groups: hydroxyls, carboxyls, silanols. These groups create polarity. Polar resins and additives are needed to achieve proper wetting. Ignoring polarity leads to partial dispersion, poor gloss, and film defects. Third, hydrogen bonding. Some pigments have active sites capable of hydrogen bonding. Resins or additives with complementary groups improve wetting and stability. Mismatch causes flocculation, clumping, or pigment agglomeration. Now, let's consider particle size. Fine pigments are more sensitive to interaction mismatches than coarse pigments. Smaller particles have higher surface area, amplifying molecular forces. A mismatch that seems minor for a coarse pigment can lead to major defects with a fine pigment. This is why minority-thinking engineers always consider both pigment chemistry and particle size in their calculations. Next, let's discuss additives and dispersants. Dispersants are not just helpers. They modify pigment surface forces to better match resin characteristics. A dispersant that balances dispersion, polarity, and hydrogen bonding moves the pigment point closer to the polymer in Hansen space. This reduces Ra distance and lowers red. Experienced formulators use this approach to optimize dispersion systematically rather than empirically. Now, consider pigment-resin ratio. Increasing pigment load changes overall interaction balance. High pigment concentration shifts the effective Hansen coordinates of the system. Solvent or additive adjustments may be necessary to maintain red 1.
Here's an example.
An automotive primer uses titanium dioxide. The polymer has a solubility sphere centered at specific delta D, delta P, delta H values. The pigment surface interactions sit far from the polymer center. Without a proper dispersant and solvent blend, red exceeds 1. Result: flocculation, poor opacity, settling. With proper calculation and adjustment, the effective pigment-resin system moves closer to the polymer center. Red drops below 1. Dispersion stabilizes. Opacity and gloss are optimal. Next, we address multi-pigment formulations. When 2 or more pigments are present, each has its own coordinates. The overall system is the weighted average of pigments, resins, solvents, and additives. The minority-thinking engineer calculates or estimates the net position in Hansen space to maintain compatibility. Now, a common mistake to avoid. Some engineers believe pigments only interact with resin. But pigments also interact with each other. Hydrogen bonding and polar interactions between pigments can lead to aggregation. Dispersants help, but understanding the underlying forces is critical. Another insight: temperature matters. During mixing or drying, temperature affects solvent evaporation and molecular mobility. Pigment-polymer interactions may shift relative to the polymer's solubility sphere. This can lead to temporary flocculation or instability during processing. Minority thinking engineers account for this by selecting solvents and dispersants that maintain red 1 under expected conditions. Now, let's tie this back to previous episodes. Hansen theory for solvent design is only part of the picture. Polymer behavior defines the solubility sphere. Pigment interactions define additional constraints. Additives and dispersants fine-tune compatibility. Scale-up and environmental conditions test the robustness of your design. This is a multidimensional problem, and Hansen theory provides a framework to manage it, not a simple formula to follow. Here is the mindset shift. You are no longer adding pigment and hoping for dispersion. You are engineering pigment-resin interactions in molecular space. Every choice you make, solvent ratio, dispersant type, pigment grade, polymer selection, moves points in Hansen space. Your goal is to keep the system inside the solubility sphere. Your goal is to minimize RA distance. Your goal is to maintain red 1 under all processing and environmental conditions. This is predictive formulation, not empirical luck. Finally, let's connect this to performance. Proper pigment-resin compatibility ensures uniform color, high gloss, stable opacity, reduced settling, consistent rheology. Improper alignment leads to defects. Flocculation, pigment floating, haze, a film defects. This is why pigment-resin interaction is a critical application of Hansen theory. In the next episode, we will explore crosslinking and curing interactions in Hansen space. We will see how polymer networks and solvent systems interact during reaction and how Hansen theory guides robust coating design. If you want predictive pigment dispersion and full formulation control, stay with this series. This is Hansen theory.